Thank you very much. There is actually in the UK an analogue of the Henri Poincaré Institute with which we have quite close links, and quite fittingly it is named Isaac Newton Institute. And it's my special pleasure to be here in this place in which so many great scientists of the past and the present have been giving lectures, public lectures like this one, intended for non-scientists in particular, to give a glimpse of what we do in research. Let me emphasize that this is a problem of interest for all society, not just scientists. How is science done? You may know or not know that a few years ago, the Wall Street Journal had this weird idea to do a ranking of all the existing jobs in the world. Nowadays, it's quite in fashion to rank everybody, richest people, best universities, whatever. So they went for this ranking of jobs, using several layers of criteria and asking in terms of career opportunities, in terms of growth, in terms of impact, happiness, whatever, everything. And what arrived first was not obvious guesses like trader or princess, but mathematician. So see here, admire the mathematician here, all happy in the peak of abstraction. Here was poor lumberjack who was ranked as the absolute worst job. Maybe some of you have family doing lumberjack, then please don't take this ranking seriously. Except for the first rank, which does have quite some truth to it. Notice more seriously that several of the first jobs here in this ranking are specialized scientist jobs and related in a way or the other to the current revolution of computer science, big data, statistics, whatever. By the way, in 2014, a team related to this team of the Wall Street Journal performed the ranking again and arrived at the same conclusion in 2014, mathematician number one. How do these people define mathematician? Mathematician is somebody who applies mathematical theories and formulas to teach or solve problems in a business, educational, or industrial climate. What is good in this definition is solve problems, which is what mathematics was invented for. And since the beginning, mathematics has been used by mankind to solve problems. Problems of geometry, problems of economics, many kinds of problems. It has been used since the beginning in this way, and all the more nowadays in a world which is becoming more and more mathematical with the advent of computers. At the beginning, computers have been imagined by mathematicians and devised, mathematicians and engineers. We all know that Alan Turing is often considered as the father of the modern computing era. So this was a domain in which there were the mathematicians bending over the baby's nest, like the fairies in the tale. And then the baby grew and grew and grew and is invading everything. It was estimated in a study a few years ago that mathematical research accounts for 16% of the English gross value added of the economy. And this percentage is poised to increase and increase as the power of computer science is increasing also. Computers being such a great tool to act as a resonance system for mathematical theories. However, you heard well when I said about this study, it was about mathematical research. Mathematical research does not completely fall into the definition here. Applies mathematical theories and formulas to teach or solve problems, that's good, but there's also the job of creating new mathematics. That's for people like me or the hundreds of thousands of other mathematicians around the world, whose job is to produce new theorems. And let us insist on this, that mathematics has never been so active as a field, creating new theories and new theorems. But how is it done? Here you have this beautiful picture, mathematician #1 job. Here we have this impression of so many innovations and inventions and so on, depending on mathematical research. But it's not that easy when you are looking for the new idea. What is, however, remarkable, and here we are helped a lot by the structure, the very structure of mathematics, is the fact that by definition, mathematics is an abstract field. What is abstract may seem like it's something very remote, difficult to apprehend, but there's another side to it. What is abstract is very powerful because it can be incarnated, if I may say, in very many different problems. And this can go over for the centuries and the centuries. Just to take one example, which is emblematic of nowadays world in which we are swimming in an ocean of information. Take the good old Fourier transform, which was invented in the beginning of the 19th century as a way to extract the frequencies for a signal. And it was at first used to analyze the variations of the heat. That was the goal of Fourier, study the variation of temperature. What happens when you heat some metal device and you wonder which will be the rate of cooling and so on. And later, it was used to analyze, say, the songs of the birds, because you can extract frequencies for the songs. And it was used and is still used to analyze images. Take the beautiful image here, famous Lina from graphics. And here is the Fourier transform. Maybe a bit less attractive, but extremely useful to transfer information and propagate it and act on it. Also because of its redundancy. And it's the same Fourier transform which is also used in a scanner, Raman imaging device that you use in medicine. So one single technique and idea will have many, many ramifications in many very different fields. And that mathematics is the field in which this can happen most easily. So that's one advantage and at the same time one disadvantage. How to make the link between the theory and the applications. In many cases, there is no possibility. Fourier had no way of guessing that his invention would be once used to study, for instance, what goes on in our brain through Fourier transform of the cerebral activity. But he had this idea that understanding can be useful. Even if you don't see the application, let's go for it. And then that's one great power of mathematics, the ability to transform research that looks like pure research driven by curiosity into something that one day will find applications. However, most of the life of the researcher is not spent contemplating the good effects of the inventions. It is spent usually thinking like crazy and failing to understand. Most of our life is spent in failure. I'm sorry to say it, but that's the truth. And in most creative jobs, that's also the case. And we have to understand this. You have to accept this. It's a job of constant frustration. And here we are in this typical scene, thinking, waiting for good old Henri Poincaré to whisper some indication in our ear. And sometimes it's really a flash of illumination, like you never know where it will come from. In my book, the book that you referred to, I describe one of these episodes. It's very striking. When this occurs to you, it's like you are the happiest man in the world. So there I was, fighting to solve some damn problem which was refusing to lend itself to solution. I was all the more motivated that I had already announced publicly that I knew how to solve it. Imagine the damn embarrassment. And there I am, like crazy, desperate, scribbling and scribbling on my paper. 2 a.m. in the morning, 3 a.m., 4 a.m., nothing goes out. Then in the end, go to bed in state of desperation. There's this one little brick that's missing in the reasoning. And next day, waking up, what the hell? And here in the head, hearing this voice saying, take the Fourier transform and put the other term on the other side. Wow. And that was the start of the solution, absolutely. Showing that when you are engaged in research, it's not just you thinking, it's your whole brain, including the unconscious brain. How to get into this state, we know so little about it, and still that's the crucial point. So it depends on many factors that are so difficult to apprehend. Then there's this other problem. Even when you have the right idea, you need to convince the whole world and your colleagues. Sometimes it's such a tricky thing, convince that this was the right idea. Here is not a mathematician that I put on the screen. This is Ignaz Semmelweis, one of the heroes of the story of medicine, and the first guy who understood that it was sometimes useful to wash one's hands, especially if you are a medical doctor and ready to give birth to some baby, and in the time between the one you are cutting corpses to study in between them and the time you are delivering a baby, it may be useful to wash one's hands. Now, it looks like common sense nowadays, but in those days it was a matter of life and death, and Semmelweis failed into convincing his colleagues that this was important because there was no rational explanation. These people had no idea about microbia and microscopic organisms that we are familiar with. It looked like esoteric, this idea. And we all know also that even if science is very good at correcting its own mistakes, scientists are not so good. They become attached to their ideas. They really want their theories to be true. They don't want to be notified that they have erred for decades, maybe. And so it's always difficult to convince. This is true in such a field, but it's also true even in mathematics, to convince people that you have the right idea. And then there's another thing. Because you are so much into this technology, innovation, and novelty, people will think that you know about the future. This can be funny, like you are on television and people ask you, Professor Villani, what will science look like in 50 years? Tell us. What the hell do I know? Do you think I have a crystal ball? Sometimes I use this line from Poincaré. Here is Poincaré from some newspaper, it was 1900, and answering one of these questions asked by some journalist. And the journalist publishes the answer. Our famous mathematician Poincaré. Poincaré was really famous in all the nation, recognized as the best mathematician of his time and as the best French scientist, so to speak. Our famous mathematician Poincaré, so they say, has only a small number of peers able to entirely understand his works. But everybody will love this small message of him. Monsieur, your letter is arriving today. So it was a letter about what will be the science of the 20th century. And Poincaré answers, if in 1800 one had asked to some scientist what would be science of the 19th century, how much nonsense he would have said. Heavens, this thought prevents me from answering. I believe that surprising results will be obtained. And that's why I cannot tell anything about them. Because if I could foresee them, how could they remain surprising? So please excuse my silence. So this was the line of Poincaré. I have used this several times for some broadcasts. And let us say that here, I'm joking about relation to media and so on, but it's much less funny when it comes to the problem of science organizations, say at the level of a state or some governmental organization, asking you to make a plan to justify the money that you will receive, and you will do this after 1 year, this after 2 years, this after 3 years, and so on. And much of the time, you don't know what you will be doing. In my career, most of my good result was obtained not so far, not so long after I got aware of the problem itself. Sometimes it's the unexpected, which is the most interesting. It's important to recall this always. Now let us dig in the Poincaré answer. When Poincaré says, I believe that there will be some surprising results, it looks like a bit of a joke, but it's more like that than that. It's like asserting, as a kind of philosophical belief, the confidence into the capacity of mankind to always come up with new surprising results. And the fact that the next generation will understand more than what we know and will be more clever in a way than what we have been doing. And that's an important thing also. That's a very important thing. And let's dig on this, if you allow, in the remaining of the talk and ask about this process of how the new ideas will be born and come and get better than the older ideas. Let us illustrate the extreme power that the abstract ideas can have in our real world with some famous examples from the past. I already alluded to Alan Turing. As you know, there is the Hollywood movie coming out these days. And Alan Turing is remarkable in many ways, but in particular, okay, it is good that the movie is out to remind people of the role that mathematics had in Second World War. It is estimated in particular that without the particular contribution of Turing and the breaking of the Enigma codes of the German army by the English, the war would have lasted at least 2 more years. It would have been impossible to make the operation in Normandy in 1944, and many of the operations would have been completely different. Think that during all the war, even though it was such a tough war, the Allied were able to, the English and Americans were able to read and know every communication from the Germans. Imagine what it would have been without this advantage. Next to Alan Turing is Paul Erdős. He is a symbol of a very important move of ideas which took place in the 20th century. So Erdős was a Hungarian Jew, a mathematician, the most prolific mathematician of the 20th century. Also remarkable for his particular way of living, with no family except his old mom, no house, no car, no job, just one suitcase, you know, and going from house to house, from colleague to colleague. Little money that he gained in mathematical prize, he would redistribute it, offering solutions to some other mathematical prizes, and really not caring about anything except new ideas, new theorems. Erdős is so famous that mathematicians have invented a number called the Erdős number, which is the number of collaborations you need to go from you to Turing. If you have collaborated with to Erdős, sorry. If you have collaborated with a collaborator of Erdős, your number is 2, and so on. And they study this graph and so on, so he's a mythical figure. But also a symbol of this huge immigration wave of brains, of ideas which took place also around the time of Second World War with the persecutions of the Jews and so on, from Europe to America. And it changed the face of science, the face of the world, and made America emerge all of a sudden on the planet of science, let us say. Erdős and his many, many friends represent one of these stories which was of paramount economical, scientific, cultural importance for the world. So that was Erdős. And let's continue with another Hungarian Jew to his left. This is Leo Szilard. Who in this room has heard of Leo Szilard? That's not bad. So, Szilard, among other accomplishments, was the first human being to think of the principle of the atomic bomb, chain reaction. And this happened here in the streets of London. He described famously how the idea came to him as he was waiting for a red light to turn green. Like, it's again one of these things. Even more interesting, he was trying like crazy to disprove a statement by Rutherford, who was the godfather of atomic physics. And Rutherford had claimed in some conference, you know, there is some energy in the atom, but it's tiny, tiny. Anybody who would think of exploiting this energy would be talking moonshine, be a lunatic. And Szilard was very angry at this comment. You know, he was the kind of guy who did not like established ideas, wanted by principle to provoke and to contradict. And so he thought hard, how can I prove Rutherford to be wrong? Just for fun. How can I prove? How? And one day, puff, the idea of chain reaction coming. This was 1933, so long before the principle was indeed started. Later, Szilard, after emigrating, also him, from Germany to Austria, to UK, to US, and he is the one who made Einstein write the famous letter to the President of the United States, which started the whole Manhattan program about the atomic bomb. In the end, 100,000 people working on this problem within a few years. All started with just the right idea. So in these examples, we see how powerful these ideas may be, and we see also how important can be the role of one individual. One brain flashing like this or not like this can have dramatic consequence, because then by human organization it will be amplified by thousands and thousands of people. To the left of Szilard, I put the patent which he filed with Fermi for an atomic reactor. And here at the extreme left, I put the image of one of the most famous universities in the world to recall that thing that one always has to keep in mind, and which is echoing the Poincaré statement: the value of a higher education institution does not lie in the fact that students are taught the best science of the day. It lies in the fact that its students will be able to get ideas that go further than that. So it's not in the quality of the teaching, it's in the fact that it will trigger the students to get the ideas which their masters did not have. That's the key, absolute key problem, how to foster the creativity, and nobody really knows what is the rule to do that. So it's the most important problem in this business of ideas. It's of paramount importance, but still, how does it work? We're not so sure. Poincaré, in one famous writing, tries to describe some of the circumstances behind the birth of ideas. And he insists, I gave already a few examples on this, but Poincaré is the one who puts it in writing most clearly, maybe, about one episode in which, after, you know, fighting like crazy for days against a problem which does not give up, he's going on a hike with some friends, and when he's back, at the very moment where he sets foot on the marchepied, where there's this small scale, so as to get on the bus again, at this very moment arrives the idea, which was the solution of the problem. And this episode is quite well known for people interested in cognitive sciences and so on. Here is another of these texts in which he describes his experience. Disgusted at my failure, I went for a few days at the seaside and was thinking something completely different. And one day, while walking on the cliff, the idea came to me with all these characters of brevity, its sudden, and its immediate certainty that arithmetic transforms of quadratic ternary forms indefinite are identical to those of non-Euclidean geometry. Probably not all of you understood exactly what he has in mind, but still enough to see that there's nothing to do with the cliff. It's one of these things that it always takes you by surprise. By the way, I see that there are some young people in the audience here. Keep this in mind if someday you have some homework or some composition, some exam to prepare, and you need absolutely to go and see your friends at some pub or something. You may try to tell your parents that you are applying the Poincaré method. You heard this in the talk of this French mathematician, you know. So anyway, that's this problem with that Poincaré is setting us. If this is so difficult to foresee, how we're going to make it so that the discovery takes place? I did a bit of the Poincaré exercise with the book that was mentioned in the introduction. Birth of the Theorem is the English title. Theorem Vivant is the French title. Let's comment on this, by the way. My initial title was Naissance d'un théorème, which literally means birth of a theorem. And then the French editor said, wow, this is too explicit. We need something a bit more dreamy, more not so explicit. So I thought, and in the end I thought, okay, théorème vivant, living theorem. I like to insist on the fact that it's mathematics is a living field, that it's done by living people. Maybe people will mistake and think that I am the living theorem. Maybe, of course, it also insists on the fact that the theorem is the hero. And also I was thinking of a book I was reading when I was a child, a Disney book called Désert Vivant, Desert Lives, in which you would see photographs of the desert and animals that there are in the desert. And I thought, yes, it's like this. In mathematics, people think mathematics is like a desert, that it is dead, has not changed for hundreds of years, if not thousands. But if you know where to look, you see how much life there is. It's just like in the desert. Then it was transmitted to the English editors, who made a beautiful work, by the way. But they said, wow, Théorème Vivant, it's not explicit enough. Why don't you do it birth of a theorem? I said, okay. Let's do it. I thought it was a nice illustration of the usual slight difference of taste between one side and the other of the channel. So birth of the theorem is what it really is. Or let's say that the birth is like the conclusion of the book. Usually when we talk about science outreach, we talk of ideas which are already born, we talk of theorems, and here is how to use it, and that guy invented this, and we can use it this way, that way, etc. But you never know about what was before. Okay, we can use the Fourier transform, but how did Fourier come up with the Fourier transform? This is that the publication for a theorem is like the birth. It looks like the beginning, but in the process, cognitive process, it's rather the end. What goes on before is like the process of growing in the womb for a baby before going out in the world. And that's what I told. Not about how the use of the theorem will be made, how people will use it and so on, but how it has been conceived. First chapter is like a fecundation. It's discussion between myself and my main collaborator and former student, Clément Mouot. And in the process of discussing, while we are trying to solve some problem, the Boltzmann equation, we say, hey, because he's thinking of another conversation he has had 2 years ago with some guy. I'm thinking of another conversation I had 2 years ago with another guy. We put this together to say, hey, we should be working not on this problem, but on that problem. And that was the very start, the precise moment in which we embark to work on this problem of nonlinear Landau damping. And then it goes on for 2.5 years until the time when the theorem is proven and is published. What happens between this is this gestation process, and it's a complicated process, full of mistakes, Many times we believe it's like this, and then in the end it's like that. Or we go on, find the right argument by the wrong reasoning, or discuss with some guy and he has an idea which does not work but leads us to the right path, and so on and so forth. Many pieces of luck, many interactions, talking with people, many times when we are discussing alone, many conversations, and so on. And this process is the usual life of the mathematician. It's much more about fighting the problems than about solving them. I recall recently a public lecture by some specialist of epistemology saying the job of a scientist is not so much about knowledge, but about the unknown, about fighting with the unknown all the time. It's not about knowing things. And that's precisely what you see in this book. And I also wanted it to be the very accurate reflection of what is the atmosphere when you are doing this fight. So the conversations, unfiltered with the technical words, as in the Poincaré text, by the way, and removing any possibility for the reader to try and understand what the mathematical concepts are. If the reader starts thinking, what does it mean, Boltzmann equation, this or that, there will be some loss in the audience. Some people will become lost. So let's make sure that they don't try to understand the mathematical concept. No explanation, but insist on the facts, on what happened, the atmosphere and the feelings and the emotions, and also the environment. The environment can be what kind of music you're listening to when you are working, what kind of moves you are doing, which university you are going to, and so on and so forth. And I usually say, the usual way to do mathematical outreach is to simplify things and use words and analogies that everybody understands. Like you would do to explain your child what is your job in words that the child may understand because it refers to what the child is used to. But there is another way to explain your child what you are doing at work. It's to take your child at work, put him on some or her on some nice chair, and just do your usual activities. The child will not understand a single word for many jobs, but see which are the reactions, the tension, the anger, or the feeling of happiness, the interactions, and so on and so forth. And that's exactly this second approach which is taken in the book. Like if you are the little mouse on the shoulder of the mathematician, witnessing every of their reactions. So that was the idea of Theorem vivant, birth of the theorem. Now let me, however, say a few words about what was the problem about, but just a few words. The problem was dealing with mathematical physics, as does most of my research, and it was a problem about plasma physics. Physics and mathematics are so close to each other, and have been so for hundreds of years. And it's normal, because in physics you have situations which are relatively simple and can lend themselves quite efficiently to mathematical treatment. Now, what is a plasma? A plasma is like a gas in which the conditions are such that electrons have been separated from the nuclei. The electrons are charged negatively. So as we learn in school, the electrons will repel each other. And they are very small, very tiny, even at the scale of the atom. Very light, so very mobile. They move very quickly. So these electrons form a kind of cloud of fast-moving, repelling particles. And it's important for anybody working in plasma physics to understand how this cloud of electrons is moving. There are many applications of plasma physics. It's a state of matter, like gas, liquid, or solid. It's a state which in the universe is very, very frequent, but has been discovered much later than the other states. And for instance, to quote just one example, people working on nuclear fusion and trying to control them for getting new power plants of a new kind need to understand the properties of these plasmas. Now, plasmas are governed by equations of statistical physics. the trajectory of one plasma is very difficult to predict, of one electron, sorry. But the statistical behavior of these electrons can be predicted very accurately. And we know the equations since the beginning of the 20th century. It's part of the field of so-called kinetic theory, which was founded in its modern way. I'm glad to quote here, was founded by Maxwell around 1867, something like that. Now, in the 1940s, Lev Landau, who was a great Russian scientist, came up with a very revolutionary suggestion about plasmas. He was a tough guy, and he says, you guys have understood nothing about plasmas. And he was saying plasmas are quite stable objects, which was a surprise, because in plasma there is none of the usual mechanism for stability. Stability is the fact that after unrest, typically something will come back to rest. Like, for instance, this is my cell phone. If I send it like this, according to the laws of Galileo, it should go forever and continue and make some parabolic trajectory and so on. It does not because of the friction, acting as stability factor. Most of our life is dominated by friction as a great stabilization. This and the fact that we are all attracted by the Earth are the two main factors of stability for us. But in a plasma, there is nothing like this. No friction, no phenomena, like physicists would say, with increase of disorder, increase of entropy, which act to stabilize things, no dissipation, and so on. And nothing that would make all electrons go in the same direction. So it was well admitted that if you have a disturbance in your plasma, it would kind of go on forever without any mechanism to prevent it to do so. And then comes Landau saying, you understood nothing, there is stability mechanism, and here is the mathematical reasoning for that. And that was a shock. This is called Landau damping. It is estimated that about 1/3 of papers published in plasma physics appeal this Landau damping effect. So it's tremendously important for plasma physicists. Still, resting on very fragile theoretical ground, Landau established it only for special case of so-called linearized plasma, in which you neglect all linear and nonlinear effects and work with a simpler equation. And it was debated among physicists, among mathematicians, whether you could go on with the nonlinear effects with that. And that's the problem that we solved, Clément Wu and myself. We proved that even in the nonlinear approximation, this Landau damping does occur. In itself, you may say it was just confirmation of what physicists expect. But not so much. First, it was debated, even among physicists, whether this was true or not. And second, as usual, what we like in mathematical physics is when the proof gives you new information about the physical mechanism. And it was a long, complicated proof, full of surprise. We had no idea of how rich it would be before embarking on it. In the end, the result is a proof made of mathematical formulas and reasoning. The paper was 180 pages long, all this to prove only one theorem. And as I always say, well, when you're a mathematician, it's your job sometimes to put together a proof of more than 100 pages long. And it's better to have started at an early age training on small proofs with triangles and lines and circles of 10 lines. Anyway, that was the Landau damping contribution. We found on the way connections with problems. For instance, we found a connection with the problem of the stability of the solar system, an old problem which started with Newton and was studied by other people like Poincaré, Laplace, Kolmogorov, and many others. It seems completely different, stability in a plasma and stability in the solar system. But in the mathematical world, there are connections. Later, it was found that our contribution also has applications to the problem of stability of fluids, while it's a completely different physical world. Even there, the power of the abstraction is present as something that can be applied in various directions. So far, that's all for what we did from the mathematical point of view. Let me mention in passing that birth of the theorem is the story of this idea coming up to the world. So the idea really is the hero of the novel. And you have to imagine that you will see it grow little by little from the stage in which it is very disorganized, just thoughts in the conversation of the mathematicians, to the state in which it is very organized, ready for publication. And there will be excerpts with big formulas, which are not here for the reader to understand what the formulas are about, but to contemplate and appreciate this growing of the idea and the theorem from this very chaotic stage to the final, very organized state. Now, at about the same time appeared this book, by the way, beautiful book by English scholar Francis Pufford, Read Plenty, in which also the hero is an idea, but at the scale of a whole economy and several decades. The idea of mathematical planification of the economy. Leonid Kantorovich, one of my personal heroes, is one of the main mathematicians in the novel, and this is the Soviet economy viewed from the pipe of mathematical planification, from the boom of the 50s to the collapsing of the 90s, let's say. And it's interesting to see also this abstract idea in its various incarnations here, its various avatars, and when it comes in conflict with the life of humans. Now, let us conclude with some enumeration, if you allow, of the various ingredients which are needed for an idea to grow, like the theorem which grew in the womb of the mathematical brains in my book. As I said, we don't know how the ideas come, but we know the ingredients which are mandatory for this growth of ideas. And I will list 7 ingredients, and this will be, I guess, true for many jobs related to creation and in research particularly. The first of all is documentation. In science, there is no such thing as complete novelty. You always build on the work of predecessors. And libraries have always been a very important place for reflection. In the old days, it was physical libraries, like the old Alexandria library and so on. Nowadays, it is virtual libraries, like Wikipedia or whatever. But you always need this. Can be results of experiments, can be measurements, etc. You always need these libraries. I took this example, Fadi Buno's formula. It's at one moment in the book there is some problem we have to find the formula for a problem, the iterated derivative of a composition. We don't know what it is, and I have this vague remembrance that many years ago, as I was studying in École Normale Supérieure, somebody talked to us about some formula that could be this. Had no idea what it was exactly or what was the name of the formula. But it's okay. In a few seconds, typing the right words in a search engine, you get the formula, the conditions of application, the story, everything. This has revolutionized our access to the information, but still left intact the problem of organizing it for our purpose. Second ingredient is the most important of all and the least easy to capture. It's the motivation. This is considered by many people, including myself, as the single biggest threat on the European science. Lack of motivation for the young people. And we see the numbers of people going into science careers decreasing and decreasing and decreasing. Very paradoxical, because the industry has never been so much in need of scientists, and they are wanting mathematicians, scientists, and so on, to optimize the production, to improve, to planify, etc. So motivation is such an important thing. Motivation, nobody knows where it is from. Maybe it is when you are a small kid that the motivation will come to you. It can be a teacher who is inspiring. It can be reading some book. I put here some image from a cartoon, animated cartoon named Donald in Magic Numberland or something, Math Magic Land, I guess. Well, it's a very naive cartoon, as you may imagine. I watched it a few years ago. I thought, gosh, how naive. But when I was a kid, it made me dream, really. It was one of my favorites. Maybe it's the kind of thing that motivated me to go into mathematics. You never know. You never know. Here on the left is a very interesting experiment which also took place in England, Black Autumn. Black Autumn bees, and it's about these experiments which were carried with school children. School children putting together, with the help of some scientists, experiment about bees and the combination. We discovered that bumblebees can use a combination of color and spatial relationships in deciding which color flower to forage from. And this was published in a biological journal showing that it's possible to do cool science for 10-year-old children. We also discovered, so they say, we also discovered that science is cool and fun because you get to do stuff that no one has ever done before. Signed, Children from Black Autumn. So this is important. It is usually said that in science you have to discover things that people have not discovered before. But the fact that science is cool and fun is something that is important people discover and rediscover again and again. So that's for motivation. The third ingredient is the environment. There's no such thing as an isolated scientist. It always takes place in a cultural, scientific environment. And over the history, when you see, you know, in one period it is this city which is on top of the innovation, and it's another city, at some time it's Paris, at some time it's London, at some time it is northern Italy, whatever. At some time it was Persepolis which was on top of the innovation, and it's always in an environment that these innovations take place. Or at some time it was, here I put a picture of Budapest, because what happened in the minds of Hungarian scientists in the beginning of the 20th century changed the face of the earth. And there was this ecosystem, extremely innovative, in which culture and ideas were put together. So there is always this ecosystemic view we have. The institute which I am director of, Institut Henri Poincaré, lives on this ecosystemic view. Our goal, our mission is to attract and invite hundreds of researchers every year in mathematics and theoretical physics and put them together within the Paris ecosystem so that new ideas will come out of this. We don't know which ones, but putting together is important. And nowadays, even 21st century, the idea of physical presence is still important for all these things of research and innovation. By the way, the book Birth of the Theorem was born through an ecosystemic thing. I never would have by myself the idea to write such a book. But in some dinner, you know, cultural event, I met this editor. And he said, wow, who is this guy with his spider? Let's see. And we discussed, and he was saying, oh yes, I heard you're a mathematician, you're interested in... We are in need of a book for mathematical outreach and so on. He was... his company was specialized in literature and so on. And I told him, yeah, maybe I could write a book about entropy because I'm one of the world experts. It's so important for this. But he didn't care. I told him I could write. He didn't care. He said, I just want to know what is your life like, daily life? What do you do? How is it? What's the emotion like? And you know, through this encounter in some cultural event, the book was born. It's also because I was incorporated into this ecosystem. Now, the next ingredient is communication. It's a bit different from the ecosystem. Ecosystem in particular is here to make the new ideas arise. But then when you are doing your project and it's many actors together, you need smooth and fluent communication between the various collaborators. In particular, in my case, in the case of this Landau damping, most of it was done across the ocean, literally, as I was in Princeton visiting and he was in Paris, and we were exchanging emails daily with a lot of information. Some of them are reproduced in the book, and it was really like delocalized brain, so to speak. The power of the communication at rapid speed makes it possible to do these things. Now, here's a very interesting experiment set up by Tim Gowers from Cambridge. He was a Fields medalist some years ago, and he put up these experiments of massively collaborated mathematical project, in which hundreds of mathematicians worked together on a single theorem. He did this, and his colleagues also did this for several problems. In the end, they solved several of these problems with so the article was authored by this entity, which they called Polymath, which was the collection and collaboration of all these various brains, thanks to the fast communication. The next ingredient are the constraints. For many people, it's complete shock, but for other people, it's complete triviality. That constraints are very important for creativity. If you don't have the constraint, you're not motivated to find something that is new. And in mathematics, we are so much constrained by the need to have some completely rigorous argument, leaving zero place to possibility of the contrary, that this is a field in which we have to be extraordinarily creative. One can draw a parallel, by the way, to other forms of art, like poetry is traditionally one which is realm of imagination, but also the most constrained in terms of rules of how you write the poetry and so on. I gave here, to insist that it is also constrained in other fields of art, two of the pieces which I like very much, which are a result of very creative works coming from unreasonable constraints. This is a piece from Musica Ricercata of György Ligeti, another of these Hungarians who was raised in this scientific atmosphere but turned to music. In this Musica Ricercata, in the first piece, there is only the note A, you know, like in ABC, but this is only A's, except for the very last moment. And you see this, you say, gosh, it has to be the most boring piece ever. And it is not, because the constraint on the frequency forces you to find all kinds of creativity in the rhythms, in the whether it's strong, whether it's piano or forte, etc., every possible thing. And so it's very creative and enjoyable pieces that this is. And here, this is another very constrained piece from a famous novel, La Disparition, Disappearance, in which Georges Perec wrote this thick novel with no letter E. So, of course, this gives a kind of special new language that resembles nothing else that has been written in French language. Crazy constraint giving rise to something quite new. In mathematics, we have these notions of very strong constraint. Next, I already talked about it. The next ingredient is the intuition, and rather the combination of intuition and hard work. In the Poincaré examples, he's not describing a process which is working like crazy systematically, but it's neither a process of waiting quietly for the solution to come. It's a combination of both. It's working hard, and this is in periods of working hard and alternated with periods of illumination, relaxation, in which the solution comes. And last ingredient is combination of luck and perseverance. They come together, because if you don't try, you never have luck. But it's very often said, I told you, it's most of the time failure and sometimes piece of luck. And one of the most important qualities that a researcher must have is recognize when there is some element of luck popping up. This must be maybe the most important of all. One example I learned from what was maybe my first significant mathematical contribution. I was 23, 24, something like this. Young researcher in my PhD, going abroad for the first time as a mathematician, in an Italian lab. And the director of the lab had a problem for me. We had met some months before. I had shown him a mistake in one of his papers. That's a very good way to become friends. And when I arrive, he tells me, look, I have this idea to solve the Cecchiniani conjecture, try it, and we'll see what it goes. He was the head of his laboratory, so he had no time for research and was absorbed in meetings. I was PhD, so I had all my time, and I worked out for hours. And then I see after a moment that this idea was nonsense. And it was so naive, impossible to make it work. But in the process, I noticed there is this weird computation giving up some nice result. This nice identity came out of the computations. Maybe that's the important thing. And I thought it's too beautiful to be useless. And this was indeed the start of the solution. Came by accident, kind of, while trying to work out some nonsensical idea. Here comes the important thing, and I recognize this is the piece of luck I can thrive on. So that's all for the ingredients of the ideas. Let us insist that putting all this work together is no piece of cake and makes the process even more precious. Some people think that science is challenge, read science, do science, and the stuff you're taught at school. Experiment, conclusion, hypothesis, experiment, conclusion. Wow, that's not the way it works. The way it works is more like this. I wonder if here's the challenge, you find out somebody already did it, what the hell, instrument breaks, do science, not quite going as imagined, amazing results turn out to be crap, what the hell is going on? Yes, no, thinking, that's funny. Oh no, this makes sense. Ah, they figured this out 50 years ago, here we are back, and so on, and so on. And if you wanted to have some real good image, you should have to intertwine this picture, which is individual, with all the other pictures, because it's often in the encounters that the progress will come from. Let's give two final quotes, which I love, about the status of ideas. First one is from Thomas Jefferson. Status of ideas which are so precious. Thomas Jefferson is precious to use when you are in discussion with an American, because as he's the founding father, the opponent can do nothing against your quote. If nature has made any one thing less susceptible than all others of exclusive property, it is the action of the thinking power called an idea, which an individual may exclusively possess as long as he keeps it to himself. But the moment it is divulged, it forces itself into the possession of everyone, and the receiver cannot dispossess himself of it. Its peculiar character, too, is that no one possesses the less, because every other possesses the whole of it. He who receives an idea from me receives instruction himself without lessening mine, as he who lights his taper at mine receives light without darkening me. In those days, politicians did speak very eloquently. We can make a comparison with nowadays politicians. And that's the final word for Poincaré. Thought is like a strike of lightning in a long night, but it is that lightning which is everything. Thank you very much.
Is the future of mathematics mass collaboration, or is there still room for an individual genius?